Hello and welcome back, guys, to your second lesson in Unit 8, where we are going to be talking about something called galvanic cells. Now, galvanic cells and voltaic cells are the exact same thing. You're going to see in just a minute that they're also referred to as voltaic cells because they generate voltage. So you can use the term galvanic and voltaic interchangeably. You might see it both ways in any question or what you're reading. I might use both words, so just make sure you're aware that galvanic cells and voltaic cells are the exact same thing. So what is this galvanic or voltaic cell? So we've been talking about redox reactions, right? And we know that a redox reaction has two parts. It has an oxidation and it has a reduction. And so what a galvanic cell does is it actually takes that redox reaction and it splits it into two separate places. So instead of allowing the oxidation and reduction to occur in the same area, we actually split it up and have one half reaction happening in one location and one half reaction happening in another location. You might be asking yourself, why would we do that? Well, what is being transferred in a redox reaction? Electrons, right? And so what happens in a galvanic cell is that the spontaneous oxidation reduction happens, produce an electrical energy. So by separating the half reactions into two locations, so in this, what we call cell, it's really most of the time like a beaker of water, then with ions in it. We'll talk all about that. For like our lab purposes, now in real life, we're going to talk about how this is how essentially batteries work. But anyways, we separate them into two locations, and so then instead of the electrons being able to flow just directly from one species to the other, we actually force the electrons to move through this external wire. And you'll notice right here we have a voltmeter. That's because we can actually measure the voltage that's created. So by separating the oxidation and reduction reactions into two separate places, connecting them with a wire, we are forcing those electrons to travel through that external wire. Okay, so let's look a little bit more about what's actually going on here, okay? So I have enlarged this galvanic cell. We have zinc on one side, we have copper on the other side. So the zinc electrode, which is this right here, is sitting in a solution of zinc nitrate. Now, I've said this all along, I can't just get zinc 2+ ions. So I use a solution of zinc nitrate because the nitrates are spectators. They're not going to be doing anything, but they just help us. They're there because we had to use zinc nitrate to get the zinc 2+ ions. Now, on the right-hand side, we have a copper electrode, which is just a piece of metal copper, and it is sitting in copper nitrate. Again, we need copper 2+ ions. They are there with nitrates because we used copper nitrate. Okay, so zinc is going to become zinc 2+, and it's going to lose 2 electrons, okay? That, of course, is our oxidation. So we call the metal that is oxidized the anode, so that's why you see it labeled anode. I like to remember this, A and O are vowels. So the anode is where oxidation occurs. So then, of course, what has to be happening at the other side? Reduction. So copper 2+ plus 2 electrons makes copper. That is a reduction reaction, going from 2+ to 0 oxidation state. And so we call that the cathode. So the cathode is the metal that is reduced. And I remember that C and R are consonants. So that's just a mnemonic device, or that's not even a mnemonic device, but a way to remember it. Okay, so The anode is oxidation. The cathode is reduction. Okay? Now, so again, what's actually happening? So this is zinc metal. So think this zinc bar is full of zinc atoms. Okay? A zinc atom is going to give away 2 electrons. Those 2 electrons are going to flow through the wire. Well, what happens when zinc gives away 2 electrons? It becomes a zinc 2+ ion. So this is going to happen over and over and over again. Zinc give up 2 electrons, becomes an ion. Zinc give up 2 electrons, becomes an ion. Look what happens over time. We literally lose parts of that piece of metal because the solid ions or the solid atoms are giving up their electrons and becoming aqueous ions. Now, as those 2 electrons travel to the copper, now a copper neutral atom that's in the metal, it can't accept electrons, but these copper 2+ can. So as these 2 electrons come in contact with a copper ion, it becomes solid copper and starts to deposit on the electrode. And so as you see, the cathode actually starts to grow because solid copper starts to deposit onto the anode. Gosh, I keep saying anode, onto the cathode. Gosh, y'all are going to kill me. Okay, so anode oxidation, cathode reduction. Anode gets smaller, cathode gets larger. But we have a problem. The problem is as we get more and more zinc 2+ over here, and we lose more and more of these copper 2+, we're going to get a positive charge build up over here, and we're going to get a negative charge build up over here. And eventually our current's just going to stop. We have a solution. And that solution is called a salt bridge. And all a salt bridge is it's a porous material. In lab, when we construct kind of rudimentary galvanic cells, we literally just use filter paper soaked in a non-reactive electrolyte solution. So we don't want it to have anything that's going to like precipitate out with some of the ions that are in our beakers. We just want it to be totally non-reactive. It's an ionic compound. And what it does is it closes the circuit. So instead of having this positive charge buildup and negative charge buildup, which is going to happen, then our negative ions in our salt bridge flow into here to balance it out. And our positive ions from the salt bridge flow into here to balance it out. Now it keeps our overall charge neutral in our half cells, and so now the electrons can continue to flow. And here's something else to help you remember. Electrons always flow away from the anode and they come to the cathode, okay? So electrons away from the anode, they come toward the cathode. All right, so that'll help you remember it, okay? And so what's happening then is they're coming from the reducing agent to the oxidizing agent. And those terms, remember, are a little confusing, but if we look at it this way, they kind of make sense. So we call this the oxidizing agent because it is forcing copper to be oxidized. And then we call copper the reducing agent because it's providing the electrons for silver, in this case, to be reduced, okay? Now, if you notice, this time we're actually shown the voltage that's generated by this electrochemical cell. 0.46 volts are generated as the electrons flow from the copper to the silver. So again, just to review real quick, over here at the anode, we have copper becoming copper 2+ by giving away 2 electrons. Over here, we have silver plus gaining an electron to become neutral silver. Now, these are our 2 half reactions. Half reactions we've already talked about. It's just splitting up the oxidation and the reduction. okay? And remember, we always have to balance. So we would have 2 silvers taking on 2 electrons to make 2 neutral silvers. So our, whoops. Gooey line. So when we cancel out our electrons, here's our redox reaction. 2 silver plus copper, 2 plus 2 silvers. So that's a redox reaction I could have given you, and I could have said, you know, what's being oxidized, what's being reduced. You would have told me. Well, now what we did is we split it into the half reactions and we put them into 2 separate cells. Okay, so that voltage that I pointed out on the last slide, that is called the cell potential, and it is given the variable of kind of a cursive capital E. So it is the driving force. It is what causes this to be spontaneous reaction, and it comes from the pull of electrons by the oxidizer from the reducer. So remember, this one's being oxidized, this one's being reduced. So then this itself is the reducer, and this is the oxidizer. Because the silver is forcing the copper to be oxidized, the copper is reducing the silver, okay? It's tricky. You just got to kind of keep saying it over and over again, okay? So the cell potential is also called the electromotive force. The unit is in volts. It's important that you notice that it's 1 joule of work per coulomb of charge. That's going to be important in a little bit, because we're going to see that even if we have to multiply the reaction through by a coefficient to make the electrons balance, we don't multiply the voltage, and that's because it's per coulomb of charge. So no matter how many we have, it's still per coulomb of charge. And we can measure it with a voltmeter. So we would actually see we have voltmeters. If we set up a galvanic cell and we attach the voltmeter, we will actually be able to read the voltage that's being generated by the electrochemical cell. Now, scientists went through and they determined the standard reduction potential. So we have our variable for voltage, or the electrochemical force, and then we have that degree sign that we know now from past units means standard, okay? So the standard values correspond to reduction half reactions with all solutes at 1 molar, all gases at 1 atmosphere. So that just means that's the standard set of conditions. So the way that scientists determined all of these standard reduction potentials is they use something called the standard hydrogen electrode, or the SHE. So they used the hydrogen electrode as a reference point. So we set the hydrogen electrode as 0. Okay, so this is kind of similar. You can think about it like the temperature scale, Celsius. We said, okay, wherever water freezes, we're going to call that 0. And then everything else is compared to that. Same idea here. We did the reduction potential of hydrogen, we set that as 0, and then compared everything to it. Now, hydrogen, of course, is a gas, right? And so you can't have a solid electrode of gas. So instead, what they use is they use a platinum electrode, because we've got to have metal, attached to a wire so the electrons can flow through it. So we use platinum because it's totally unreactive. And then you'll notice that platinum electrode attached to the wire is inside of a tube that we bubble hydrogen gas through. Okay, so that's where we get the hydrogen gas. The platinum electrode is just there to pass along the electrons. And of course, here's the reduction reaction for hydrogen. Okay, and so then we see that its standard reduction potential is 0 because we've set that as the baseline. So then what scientists did is they constructed a galvanic cell. They always use hydrogen as the anode. And then whatever other metal they were looking at, they used as the cathode. Okay? So then we'll see in just a moment that in order to calculate the voltage of any cell, or the cell potential for any galvanic cell, we do cathode minus anode. Okay, so basically we're saying what is the reduction potential of the cathode subtracting the anode, which is being oxidized. It's kind of like it's working against it. All right, so we subtract cathode minus anode. Well, if we have set this as 0, then the voltage of the cell just equals whatever the voltage of the cathode is. So by setting this to 0, any voltage generated is being generated by the reduction of that metal, which then, for this example, means that copper's standard reduction potential is 0.337 volts. So in just a second, I'm going to show you a whole standard reduction table, but I wanted you to understand where those values came from. Now, hydrogen gas is very flammable, so it's very dangerous, so it's often not used in labs, and so that's why this was kind of done in very controlled environments for us, and then now we use the table. So here's the table. As I mentioned, these are the standard reduction potentials, so a couple things that you need to notice. If they are standard reduction potentials, every reaction here is written as a reduction. Because it's what voltage that metal or ion or compound generates compared to the hydrogen electrode. So if you notice, our hydrogen electrode, remember that was our 0. So anything above that has a higher voltage, has a higher reduction potential than hydrogen. Anything below it has a lower reduction potential than hydrogen. So you'll see that that's why after hydrogen they become negative. Okay, so then anything with a higher reduction potential can work as a reduction, and anything below it would then have to be an oxidation. Okay, so we can use all of these standard reduction potential values to allow us to calculate the standard reduction potential of any galvanic voltaic cell. Okay, so if we are given a cell, then we are going to have to find the reduction potential of both half reactions. The higher or the larger potential is going to be the reduction because it has the higher reduction potential. It's going to run as it's written on the reference table. The other half reaction will be reversed. It's going to run as the oxidation. And then the net potential, or the overall cell voltage, is then the cathode minus the anode, or in other words, the one being reduced minus the one being oxidized. Now, if we're trying to balance out the reaction and we have to multiply through by a coefficient to get our electrons to balance, remember I mentioned this before, we do not do anything to the cell voltage. The one that flips, we don't change the sign because our equation takes care of that, minus the anode. So it reverses it for us, okay? And so remember, it was joules per coulomb of work. So even if we have to multiply through by 4, it still creates the same voltage per coulomb. Okay. So let's look at an example. So we've got iron 3 plus copper yields copper 2 plus iron 2 plus. Okay. So the first thing that we're going to do is we're going to separate this into its half reactions. So we have iron 3 plus yields iron 2 plus, copper 2 plus yields copper. Now we got to put our electrons in there. So it's iron 3 plus an electron, and copper 2 plus 2 electrons. Okay. So what you can do if you need to is you can actually look at your reduction potential table and you'll see these reactions written out for you. Now notice right now I have both of them written as the reduction. Now when iron 3 plus is reduced, its voltage is 0.77. When copper 2 plus is reduced, it's 0.34. So remember, the higher voltage is going to be the reduction. The lower voltage is going to then flip and run as the oxidation. Okay? So this one's going to be our oxidation. So if we want to make sure we kind of visualize what's going on here, if I have two beakers, so my two half cells, now I want to point something out while I'm doing this, that a lot of times we do anode, cathode, but that doesn't mean it's always going to be left to right. It is possible that the cathode could be on the left and the anode could be on the right. So don't get tripped up by that. It's just, typically speaking, we do cathode on the left, or anode on the left and cathode on the right, but it is not always. Okay, so anode, we remember, is our oxidation. So that means that it is our copper. This is my voltmeter, connecting it to then the one that's running as the reduction, which is the iron 3+. Okay? So the oxidation reaction, remember, we have to flip that one. So it's copper goes to copper 2+ plus 2 electrons. And then iron 3+ plus an electron makes iron 2+. We had to multiply the iron one through by 2 to make our electrons cancel out. Okay? And so what's happening is each copper is giving up 2 electrons. They're running through the voltmeter, running through the wire over here where the iron is being reduced. Okay? So then we always do our cathode minus our anode, so 0.77 minus 0.34. So the cell voltage for this cell is 0.43 volts. Okay? Okay, so before we go on and practice a few more examples, I'm going to show you something called line or shorthand notation. And this is where if instead of like having an entire cell drawn out, or maybe even instead of giving you the equation, they just give you the shorthand notation of the cell. So the way it works is it's always the anode, a single line, which is a phase boundary. So that kind of indicates, so going from electrode to whatever's in the solution. Then the anode solution. Then a double line, which indicates, okay, these are connected via a salt bridge, so we do have an actual operating cell here. Then we have whatever's our cathode solution, and then that phase boundary again, which is whatever the cathode electrode actually is. So this example given to you down here is the shorthand notation for this cell. So we have the anode is copper, then the solution is copper 2+, standard 1 molar. Salt bridge, we have silver plus solution, and then silver. Sometimes you're just shown the ion that is in use. Sometimes you're shown the whole entire aqueous solution that's in the beaker. It doesn't matter. It's the same thing. So if we are given this shorthand, we can write, from the shorthand, we can write our overall redox reaction. Because remember, the anode is the one that's oxidized. The cathode is the one that's reduced. So copper plus Ag plus yields copper 2+ plus silver. Now, of course, our half reactions, +2, copper yields copper 2+ plus 2 electrons, silver plus an electron, silver. that would have to be multiplied through by 2 to make these electrons equal. And so we would have 2 silvers. Okay, so if you're given the shorthand notation, basically you know that your reactants are the anode and then the cathode solution, and then your products are your anode solution and your cathode, because this is your oxidation and this is your reduction. Okay, so let's look at an example. What's the standard cell potential for a galvanic cell that consists of gold 3+ to gold and nickel 2+ to nickel? So what I'm going to do is I'm going to find both of their reduction reactions. So I've got there we go. Here's gold and nickel 2+. Sometimes you have to be careful because some metals have multiple reduction, like maybe going from 2+ to 0, maybe going from 3+ to 0. So you got to make sure you're finding the one that matches what you're given. All right, now that I have found my 2 reactions, I'm going to write them down. These are, remember, reduction potentials, so they're always written as a reduction. Voltage is 1.5, and then for nickel, it is negative 0.23. So this, of course, is the higher voltage, so this is going to be my reduction, which means that this one is my oxidation. So the cell voltage is cathode minus anode, or reduction minus oxidation. So 1.5 volts minus negative 0.23 volts, which gives me 1.73 volts is the cell potential of this cell. Okay, now if it asks you to write the balanced equation, we of course have to flip. Just didn't mean to change color there, but that works. We got to flip the oxidation reaction because it is not the reduction, it's the lower potential, so it's going to be the one oxidized. Now I got to multiply the top through by 2 and the bottom reaction by 3 in order to make both of the electrons equal to 6. So then those electrons will cancel, and I'm left with 2 Au3 plus 3 nickel yields 3 nickel 2 plus 2 Au. So there's my overall balanced reaction. Okay, one more example. This time I have iron 3+ to iron 2+. So again, we got to make sure we get the correct one. And then we have 10 2+ to 10. All right. So now I'm going to write down my 2 reactions. So I have Fe3+ plus an electron makes Fe2+, and its voltage is 0.77. And then I have 10 2+ plus 2 electrons makes 10, and it is negative 0.14. So of course this is going to be my reduction. So my cell potential is cathode minus anode, or reduction minus oxidation. So my cell potential is 0.91 volts. And if we want to write our balanced equation, there's my reduction. I got to flip the other one so that it is the oxidation. Got to multiply the top one by 2. Those electrons cancel out. I have 2 Fe3+. plus 10 yields 2Fe 2 plus Sn 2 plus. So there's my full balanced equation. Now if we wanted to construct this cell, just to give you a little bit more practice with that, remember our anode is the one that is oxidized, so that's going to be our 10, and it is in 10 2 plus solution. And then over here we have the iron, which is in the iron 3 plus solution. Of course, we'd have to have our salt bridge. So there's kind of the setup of the cell. We wanted to do it in line notation. 10, 10 2 plus, salt bridge, iron 3 plus, iron 2 plus. There's our line notation. All right, guys, so that's it for galvanic voltaic cells.